In this video, we'll look at gas stoichiometry. Stoichiometry is the study of ratios of the number of moles of substances. So, stoichiometry is based on the law of conservation of mass. So, the total mass of all products is equal to the total mass of all reactants. So, basically, if we are given the amount of one substance involved in a chemical equation, you can determine the amount of all other substances involved using a balanced chemical equation. So let's say we had a question asks us to calculate the volume of carbon dioxide in liters when 2 kilograms of propane is completely burned in oxygen. So it's a combustion reaction. And the gas volume is measured at STP. So propane, the chemical formula is C3H8. And if we write this combustion reaction out, we get C3H8 plus O2 produces 3CO2 plus H2O. No, just CO2. And now, first step is to balance the chemical equation. So to balance, we need to add a 5 to the front of the O2, put a 3 here, and put a 4 here. So what we can see from here is that for every, so this should be a 1 here, we'll just don't write the 1. For every 1 mole of propane, 3 moles of CO2 are produced, and 4 moles of H2O are produced. Now that is basically the basis of stoichiometry. So let's calculate the number of moles of propane involved in the reaction. So number of moles is equal to mass over the molar mass. So mass is 2000 divided by the molar mass of propane is 44.11. And therefore we get 45.3 moles. And we're trying to find the volume of carbon dioxide produced. And from our balanced chemical equation, we know that for every mole of propane, we get 3 moles of CO2. So the ratio between propane and CO2 is 1 to 3. In this case, we have 45.3 moles of propane, and we multiplied 3, so multiply 3 here too. So 45.3 times 3 is equal to 135.9. So the number of moles of CO2 produced is 135.9 moles. Now to calculate the volume of carbon dioxide, we use this equation, N equals volume over molar volume. And since it's an STP, we can just do volume is equal to N times 22.4. So 135.9 times 22.4 is approximately 3 times 10 to the third liters. And that's basically how you solve a gas stoichiometry question. Now, if the temperature, pressure, and stuff wasn't in standard temperature pressure, we would have to use the ideal gas equation. Okay, just keep that in mind. So that was an example of a mass to volume stoichiometry. So we were given the mass of propane and we had to calculate the volume of carbon dioxide produced. But sometimes we might do volume to volume stoichiometry. Now this is very important, and it will make your calculations a lot faster. So let's say, for example, we had a balanced chemical equation, the same thing as before. Propane reacts with 5 oxygen, produces 3 carbon dioxide plus 4 water molecules. So, and that should be gas. So this equation tells us that when 1 mole of propane reacts with 5 moles of oxygen gas, we get 3 moles of carbon dioxide gas and 4 moles of water vapor. So 1, 5, 3, and 4. And you should know that if gases are behaving in an ideal way, the molar volume of any gas is the same. So the molar volume of any gas at STP is 22.4 at STP. Therefore, the mole ratios in the balanced equation become volume ratios at the same temperature and pressure. So basically what this means is that the ratio between, let's say, propane and carbon dioxide is 1 mole to 3 moles. But it's also 1 volume to 3 volume. Okay, so if we had 3 liters of propane, let's say that, then 3 liters of propane will produce 9 liters of propane. This saves us the step from going from moles to volume and then going to the step. And by using this volume to volume stoichiometry, we can go straight to the step, which is much more efficient. Okay, so if we had a question 1, say you had methane plus oxygen gas produces CO2, carbon dioxide, plus H2O, water molecules. Now, let's say we had 50 milliliters of methane was burnt. And we need to calculate the volume of oxygen gas required for the complete combustion of the methane under constant pressure and temperature. So the ratio between methane and oxygen is 1 to 2. And we know that should be mole to 2 moles, but we also know that it's equal to 1 volume of 2 volume. So if we had 50 milliliters of methane, we would have 100 milliliters of oxygen. So we can say that 50 mils of CH4 reacts with 100 mils of oxygen. Okay, and our last question for today. So question 21 says octane is one of the main constituents of petrol. It burns according to the equation that calculate the mass of octane used if 50 liters of carbon dioxide measured at 120 degrees and 1.1 atmosphere was produced. Alright, so that's a balanced equation there. So it's 2C8H18 plus 25O2 produces 16 CO2 plus 18 H2O. So the ratio between C8 octane and carbon dioxide is 1 to 8, because 2 to 16 simplifies to 1 to 8. And therefore, if 50 liters of carbon dioxide was produced, then 50 divided by 8, which is 6.5, 6.25, then 6.25 liters of octane was produced. Now, 6.25 liters of octane is at 120 degrees and 1.1 atmosphere. And we're trying to calculate the mass of octane. And to calculate the mass, we need to first find the number of moles of octane. So using the ideal gas equation, N, number of moles, is equal to PV over RT. So P, pressure, 1.1 atm is equal to 1.1 times 101.325 kilopascals. So P is 1.1 times 101.325 times volume, which is 6.25 liters, times by the gas constant, 8.31, times temperature, 120 degrees Celsius is equal to 393 Kelvin. So 393. If we put that in our calculator, we get there we go, 0.041, so 0.0341 moles of octane, so C8H18. So that's how many moles of octane we need to produce 50 liters of carbon dioxide. Our final step is to convert the number of moles to mass. So number of moles is equal to mass over molar mass, and the mass equals the number of moles times the molar mass, 0.0341 times, now the molar mass of octane is 8 times 12.01, so that's 8 carbons, plus 12 times 1.01, 18 times 1.01, and that's equal to 3.896 grams. So therefore we can say that 3.896 grams of octane was used to produce 50 liters of carbon dioxide.